Hello friends, in this session we will be talking about what is the exact concept of space to time. Let's begin. Yes, now see here, when we talk about space to time, see here, very important. Whenever we talk about space to time means space is the input, right? Which means space is going to be the input and time is going to be the output. This is the basic we have learned. Now, you please tell me one thing. What is the meaning of space? Space input means what? Poles have to be rotated. Right? Spatial time means what? Poles have to be rotated. Am I right? Now, and in output in time means what? Yes, we know that voltage and current are what? Time displaced. So, output in time means we have to find what is the behavior of induced voltage and currents. Now, as promised earlier, in this particular session itself, we are going to talk about as to why in case of two pole, if we see the A and A dash are mechanically displaced by 180 degrees. What is the reason? We will check it out in this particular case itself. So now let's start with case 1. See here. Yeah. Now, before this, let me please tell you one thing. In this particular complete session, we will be dealing with almost 5 to 6 cases in which we will be talking about 2-pole single phase, 2-pole 2-phase, 2-pole 3-phase, 4-pole, etc. So stay tuned. It is very important. Don't skip this. Yeah, see here. Let us take case 1. Now you please tell me, when we are talking about space to time, which means poles have to be rotated, right? So let's see what is happening. For example, in this first case, what I am going to do is I am just going to take 2 poles and 2 conductors. 2 poles and 2 conductors. Let's see. As usual, this is bullseye. So representing the stator, right? Now, red is my rotor, right? So this is going to be my rotor. Let me have it like this. There is no problem. You can take salient pole or any kind of rotor. There is no problem. We are just taking it for time's sake. Let me have this as north pole. By the way, this is shaft key. This is north pole and this is south pole. Right? Now, let me take 2 conductors on the stator. Why? Because at the end of the day, induced EMF will be, taken out from the stator itself, right? So let me have 2 conductors here, 1 and 2. Now see here, very important. Since it is space to time means I have to rotate the poles in space. I am supposed to rotate the poles in space. Means these are going to rotate. Let me rotate them like this at this speed omega, right? Let me rotate them like this. Now, how will be the EMF induced in this conductor? Let me call it A. Let me call this conductor as A and this one as A dash. Do you agree that this particular machine is a 2-pole machine? Right? Now, in the immediate next discussion, we will be talking as to why this A and A dash are taken 180 degrees apart. What is the reason? We will discuss. Don't worry, time will come. By the way, you please tell me, when this is north pole, right? Which means flux will be upwards, going out of the north pole. We have known that. So, already know that for a north pole, flux is going to be outwards. For south pole, flux is going to come in. Is it right? Now, see here. Very important. Now, what am I supposed to find? Am I supposed to find time? Yes. Time means induced voltage. Now let us find. Now see, it is very simple thing. Since This is the flux, and there is some influence, and this particular conductor A will be under influence of change of flux. Why? Because this particular rotor is going to be rotated like this, which means EMF will be there. Now we are supposed to find the direction of EMF. So let's find. See here, I have already told you, in order to find the direction of induced EMF, we use what rule? Right hand rule. Not right hand thumb rule. We use right hand rule. Remember that, right hand rule. Now this finger indicates what? Flux. This finger indicates what? Direction of induced EMF. This finger, thumb, indicates what? Motion of the conductor with respect to flux. With respect to flux, you have already learned the concept. No need to repeat. See here. This is going to be the flux upward direction. Am I right? Now, see here. If this is the flux, and now you please tell me what will be the direction of the conductor with respect to flux. See here. Since this flux is going to rotate in this direction, come on, see here again. Since this conductor, see here, since this particular flux is going to move in this direction, in that direction, which means that this conductor with respect to this flux will rotate in, will move in this direction. Virtually this conductor will move in this direction. Virtually only, already we have discussed. So see here, this is going to be the flux, right? This is going to be the direction of the motion of conductor. So this is the direction of motion of conductor, and my middle finger will be now showing what? Induced EMF. So it is coming out of the board, which means it has to be placed by dot. Let me have dot here. Is it perfect? Let us do the same for this one. We know that this has to be cross, but then let us do a little bit of cross checking. See here. Now, this is a conductor, right? Now, since the flux is in upward direction, if you see here, this flux is in upward direction, right? And my rotor is going to rotate in this fashion, means, see here, this is omega, right? This is the direction of rotation, which means it is going to move in this direction, anti-clockwise. The moment my rotor is going to rotate in anti-clockwise direction, which means the flux is going to move in that direction. The moment flux is going to move in that direction, with respect to flux, my conductor will be moving in this direction, virtually moving in this direction. Now you please tell me what is the direction of induced EMF. Very simple. See here, this is the flux, this is the flux, this is going to be the direction of motion of the conductor, and into the board will be induced EMF. So here in this case, induced EMF is going to be this way. Now let us see here what are we going to discuss. Do you agree that in this particular one, when I am rotating the poles, which means input is space, what is going to happen? What is going to happen? I am going to get induced voltages in time. I will be having induced voltages in time. Now we know that, see here, for a conductor, induced EMF for a conductor is proportional to B. B is what? Flux density. See, this one we have already studied. How did it come? It came from E is equal to BLV. I hope you all have watched the video of statically and dynamically induced EMF. In that we have discussed as to why in case of conductor, EMF for a conductor is proportional to flux density. Why it is there, we have already discussed. Now see here, in this case, what is going to happen? See here, as of now, if you see, the rotor is in this particular position, wherein this is north pole and this is the south pole. Now if you observe here what is happening, see, this particular conductor A, is it under the maximum influence of this flux? Yes. Again, see here, EMF induced in a conductor is proportional to flux density, or we can say flux. Why? Because flux density is nothing but flux upon area only, no? Anyways, see here, let me come back to the topic. See, do you agree that as of now, when my rotor is placed in this particular vertical position, my conductor A is under the influence of under the influence of maximum flux density, because at the center here maximum flux density will be there. We have known this. Remember the example we have taken previously, the example of, please check the example of DC generators which we had taken earlier. Now let it be. Anyways, now see here, for A will be under the maximum influence of the flux density here, right? Now since it is north, and let me assume according to the polarity that it is my own thing, you can take it yours, there is no problem. Let me think that this dot is positive. Let me just consider that dot is going to be positive, no problem. And let me consider if dot is positive, cross is going to be negative. Let me just think about it that way, no problem. Which means, see here, because since it is north and it is in this direction, which means what? This particular A conductor will be under the maximum influence of the positive flux density. Maximum influence of positive flux density, which means A will have maximum induced positive voltage. Maximum positive induced voltage will be there in A. What about A dash? A dash will have what? A dash will have maximum negative induced voltage. Why negative? Because it is south pole, right? Just check, the direction of flux has been reversed, and that is the only reason. See, rotor is been rotating in the same direction. For this particular conductor also it was in anti-clockwise. For this conductor also it is going to rotate in anti-clockwise. Just because the flux polarity is different, here north is there, here south is there, we have found out that the direction of the induced EMF for A dash is going to be cross, which means opposite to A. So if A is positive, A dash has to be negative. I hope I am clear on this. Now see here. Now we know that these are the two conductors, and with some back-to-back connection, these two conductors will now turn into what? Turn. Let's see how it is. See here. This is conductor A. Let us say this is conductor A. And let us say this is conductor A dash. Right? These are the two conductors which I can see here. So let us say this is A, this is A dash. Back-to-back connection is going to be there. This is going to be the A, this is going to be A dash. Back-to-back connection is going to be there. The moment there is back-to-back connection, which means like this. Here I will have back-to-back connection. Am I right? Yes. Now just observe here. Just observe. See here. When I am saying A has induced voltage, I am not talking about currents. I am talking only about voltages. Why? Induced voltages. Since there is no load connected, across this terminal, there is not going to be any current. Now let us say here, see, this is A, right? Now A has dot and A dash has cross. Dot means EMF is coming out this way. E conductor, am I right? E conductor, we can say this is the EMF for this one single conductor. Now EMF for this conductor will be this way. Why? Into the board, right? Into the board. So let it go into the board only. See, this is A, this is A dash. Into the board means coming in. Out of the board means coming out. That is the direction. Now see here, this is going to be the E conductor. Am I right? Yes. Now you please tell me one thing. What will be the voltage at these two terminals? What will be the voltage at these two terminals? So for this, let me consider one thing. By the way, this is just a back-to-back connection. This is not a conductor. Mind you, this is not the active length of the conductor. We have already discussed this is not the active length. Active length means which is under the influence of the poles and in which EMF is induced. But if you see in back-to-back connection here, there is no EMF induced in this region. It is just a back-to-back connection. Please remember that. Don't forget. Now, let me tell you one thing. When this is A and this is A dash, we have considered A as dot and we are considering that it is positive. You can consider it negative also. There is no problem. You will get the same answer. Now, it is just an assumption. Why? Because we just need to understand one thing. It is not about whether it is positive or it is negative. It is about that this and this polarities are going to be different. That is what we need to understand. Now see here. If this is positive, this is going to be the negative one. 100%, right? If this is the induced EMF and this, I am considering this dot as positive, which means it has to be raised up from somewhere, which means here I should have negative polarity. Now, the moment this is crossed, this has to be negative, right? So here I will be having positive. Am I right? Yes. Now come on, see here. Let us have. What is the voltage over here? Let me consider it as V turn. Let us take it as what is going to be the voltage for 1 turn. V turn. V turn. What is going to be the voltage? Yes. Now, how to find the voltage? So, sir, it is looking quite confusing, right? Is it looking so confusing? If it is looking very confusing, just apply KVL. Don't do anything. Just apply KVL. Do you agree that this V turn will also have positive and this will be the negative one? Let us see. Let me flow one current through this like this. Imaginary current. Just for the sake of applying KVL. We know that. Now, what is the first sign test here? First sign test here is negative. This is going to be minus V turn. Right? First sign test is negative. Then, what about this conductor here? EMF is induced. This is going to be positive. So, see here. This is going to be plus E conductor for A. What will be this one? This is going to be again plus E conductor, because wherever my first sign, wherever I test this for the first time, see here. Here the first sign was negative, we took it negative. Here the first sign was positive, we took it positive. Here when the current is flowing, this is going to be the first sign. First sign is positive, that is the reason we have taken positive. So this is going to be plus E conductor, which is going to be 0, right? Back to pavilion, this is going to be 0. Now you please tell me, what is V turn? Please tell me, what is V turn? V turn, take it that way. What do we get? 2 times E conductor. Is it perfect? Now, you must have understood as to why in case of 2 pole, we are taking A and A dash 180 degrees apart. You must have understood it now, because the voltage across these turns will get tremendously increased. Because see here, when here A is under the influence of north pole, here A dash is under the influence of south pole, and that too maximum flux. See, if you see, this whole area, this half, this entire half portion is going to be under the influence of north. This entire south portion is going to be under the influence of south. So even if I place this conductor here, there is no problem. But the point is, here if you see, the flux density here will be 0. See here, I can also have a conductor here, no problem. Tetra conductor here, no problem. I can have it. This as A and this is going to be the A dash. But if you see here, the flux density influenced by this conductor is going to be less than positive maximum. Basically, if it is south, then it is going to be less than negative maximum. I hope you are understanding these points. Here if you see, air gap will be increased and all. We have already discussed that stuff. Basically, one thing you have to remember. If this is north pole here, at the center of the north pole, what will I have? I will have maximum flux density. Then less than maximum flux density, less than maximum flux density, less than maximum flux density, and here at the center we are going to have 0. We have discussed earlier. Here we are going to have 0 on this axis. Similarly, here if you see, in case of south, here at this particular point, I will be having maximum negative flux density. Then here what will I have? Some less, and here I will have 0. Less negative maximum flux density, less negative maximum flux density, and ultimately at this. So this axis is also called as, if you remember, this axis is also called as interpolar axis, also called as Q axis. Because basically, the fact is, interpolar axis, we don't call it as interpolar axis in case of AC machines. In case of DC machine only, we talk about interpolar axis or not. But for time being, you can say that it is going to be Q axis. Right. Now let me tell you one thing. This is what we have discussed regarding case 1. Now you please tell me, just concentrate here. See. The moment this one or this rotor, see here, very important. The moment this rotor, this N comes here, it gets shifted like this. See, I am rotating it in anti-clockwise direction. Now let me just shift it this way. So this N will come here and this S will come here. Now you please tell me what is going to happen in this particular position. After 90 degrees, what will happen? EMF induced in A will be what? We know when this one gets shifted here. See, this is the same one. Huh? This and this are same. This is after the rotation by 90 degrees. North pole will come here. South pole will go there. Now see here. What is going to happen? North coming here. South is going there. Here if you see, this conductor is not there by the way. Here if you see, flux density will be positive maximum. Here if you see, flux density will be negative maximum. What will be the flux density here? For this green, what will be the flux density here? 0. Which means EMF induced in A will be 0. From dynamically induced EMF thing, we know that E conductor is going to be proportional to B when we are talking about conductor. I am not trying to confuse you. I am just trying to make things clear as to what is going to happen in what case. Now, after 90 degrees, what happened? It became 0. A became 0, A dash became 0. Now, the moment this north comes here and this south goes up, what will happen? A will have cross now and N will have dot. See here. Now, when it further moves in this direction and this north comes here, S comes there. In that case, what is going to happen? A will have cross and A dash will have dot. Which means just focus on one conductor. Let us focus on only A. For example, I am sitting on the conductor and doing time pass like a lazy man. Now what will happen? The moment this is going to rotate in space this way, what will I observe here? See, let us say this is conductor A. I am just keeping it in my hand this way. And I am just trying to observe what is going to happen with this conductor. How EMF is induced in this conductor. Now what will happen? Since I am sitting there on the conductor and I am doing time pass. Which means whatever observations I will get, that will be time displaced. Already we have discussed. So when I am sitting there, what is going to happen? This particular rotor is going to be rotating, no problem. What will I observe? I will observe that when this rotor was here was the north pole of the rotor. There was maximum positive induced voltage in this conductor A. When this one came here, when this north pole in space, it got displaced by 90 degrees, this conductor EMF became 0. Then again what happened? When this north came here, south went there. Now I will have what? Negative maximum. Then again, when this, this south goes here, north goes there. This south comes here back, north goes there. What will happen? 0. Which means what I will observe? Time displaced variations or not. I will observe, right? In a conductor, what will I observe? At first there was maximum positive induced voltage when this was the case. North was there, south was here. Then I rotated it by 90 degrees. Then a conductor has 0 EMF. Now again I rotated it 90 degrees. What happened? South came here, north came here. Then if you see what happened here, EMF induced became negative maximum. Then again this south came here and this north came here. What will happen? 0, which means 0, positive max, 0, negative max, 0, positive max, 0, negative max. Now you please tell me, is it single phase? Of course it is single phase. So the waveform in time which we will get will be, for conductor A, this is let us say EA. Induced EMF in A will be what? Single phase. Now you will say, sir, but you are drawing sinusoidal wave. For time being, I am assuming that the flux distribution is sinusoidal. For time being, I am assuming. What did I say? For time being, I am assuming that the flux distribution is sinusoidal. That is the reason we have taken it in this particular fashion.